Good morning. Thank you very much for joining us today. Um, I would also like to offer an opportunity for you to join the Nikola Tesla's Today's Solution and Collaborations. This is the link and access to join. Very dynamic group of about 2,200 people that are all with the mindset of helping and collaborating and creating better solutions for people in general. Today's class will be on VFDs for irrigation pumping by the Water Pumping Institute, the good, the bad, and the ugly. And will they save you money? Presenters today from the Water Pumping Institute will be myself and Robert Welke, who I'm proud to bring along with us. He has 53 years in water pumping industry, irrigation. He comes from Australia. He has many years of experience, of actual hands-on experience. And due to the power costs that are already existing in Australia of as much as 35 cents a kilowatt, they've had to really dig deep, find some very amazing tools that can help us drastically increase our power consumption of electric motors with VFDs, pumps, in general, of getting the whole full hydraulic system efficiencies under control. I'm actually second generation. My sons now are third generation of my father, William J. Fritz, and the family in 1955 started industrial motor rebuilding in the Midwest. My father also started when he was putting up wind chargers before they even had their REA out there putting up wind chargers to actually generate power to run their radios and lights and nights at night. I also strongly believe a lot in Mr. Tesla, and I want to show a short video here next that basically talks about the technology we're going to talk about today. The reason is that electric motors consume 69% of our world's power, and it's the purchase price of the equipment, the VFDs, the pumps, the motors, all in an efficiency point, is really normally about 5% of the cost, but over a 15-year period, 95% of that cost is the actual electrical power consumed that it takes to actually operate those pieces of equipment. So it's highly important that we get this right because it does make massive changes in your utility cost.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability of alternating currents.
So what I want to start out with today is basically the electric motor is basically a rotating field that comes from our 60 cycle power. You see down below here the sine wave that is produced of voltage from your power lines, and there's 3 of these that actually feed typical motors for water pumping. The key is that the motor is going to run fixed speed, and also when it's starting wants to jump immediately to that fixed speed, because this sine wave here is pretty much permanent coming off the generators. So the generators are producing the power at 60 cycles a second. And what ends up happening is the motors, their coils here, are actually changing from north to south, and they continue to rotate, and they make the motor actually turn. So we have single phase power, which are single phase motors, which have one sine wave, which is basically two legs of the three phase power that is provided out, and it only requires two power lines out there. The issue is single phase motors on average are 70% or less efficiency. So that's why they've actually went to three phase as much as possible, but it is more costly to bring your lines out to the customer, and that ends up being about a 90% efficient device. So that's why a lot of people want to use three-phase motors, especially in larger horsepower, because there can be as much as 20% difference just in the efficiency. So I believe that if Edison and Tesla would have got along, they could have maybe created this technology even earlier. Tesla was playing a lot with frequency and frequency control, and Edison was playing with DC. So what they do is they take the three-phase power, 1, 2, and 3 as the three main lines. As you see down below, it comes in a sinusoidal voltage form. So it's coming in here. Then what a VFD is it's basically a diode bridge, meaning a three-phase bridge that lets current pass one direction. And so the ultimate resulting power is the power ends up all being inverted. Instead of being in sinusoidal, it flips these waveforms onto the top, and it gives us bumpy power. And then they put capacitors in here, and those capacitors are various sizes. And what that does is help smooth out, so we get clean DC power. They also put these line reactors, link chokes, different things. It's basically a coil, which basically reduces current flow. It wants to like hold it back a little bit compared to what the voltage does. So what that does is it again helps us smooth this DC power, because we're wanting to get firm DC power. Then the device takes and creates, with IGBT transistors, pulse width modulated power surges towards the motor winding. And this varies. Then we can control how far apart the frequency is. Like instead of being 60 cycles a minute, it ends up being, we can go clear out to 120, which will make it faster, or we can bring it all the way down to like 10 cycles, 10 hertz. Hertz cycles are the same thing. And we can also control the amplitude of voltage. So what a VFD does is it converts it from AC to DC, then back to AC with transistors that are fed to the motor. And that's really the main combination of a variable frequency drive. And that all came about because of this device at the top here, which is a transistor. That transistors were really developed, in large horsepower, large power in the 70s. Both Fuji, Toshiba were very large into it. And so once those devices were built, then all the rest of the components of a VFD are kind of like the fluff. That's what makes it know when to, how much, how it responds, how it reacts. But these are the main components that happen in order to make a VFD work. Inherently, there are losses in these components. So the average VFD operates anywhere from 3% to 5% efficiency loss based on these components that are internally in the product. So again, we have the AC coming in, feeds into the, from the diodes, creates this DC bus circuit. Then from the DC bus, it creates PWM with IGBT transistors that are all these pulses. And you'll hear things like carrier frequency. That means how many pulses per second here that they're giving. Some of them now are as high as 15,000 pulses, in here digitally firing per waveform. So it ends up being a fairly high, what they call high frequency switching. The other option that we're going to talk about a little bit today is soft starters. This has been lost a little bit because of the invention of the VFDs that have come on so strong. I still highly recommend them because these devices, once they're up and operating, they don't have any losses other than just the wire losses that you had on the original magnetic starter that shows a disconnect switch. And then this is a silicon controlled rectifier. You can see they're diodes that basically go either can feed either positive or can feed through the negative. So when the waveform goes, it passes through, but this can be regulated how fast. So you have 3 of these. There actually would be one more in there. You'd have 3 of these, in the circuit feeding to the 3-phase motor in a soft start controller. The main focus of this is to eliminate the high inrush current. So when you go put 460 volts initially, right, like a starter did, right to the motor winding, the motor ends up, because it's not up to speed, comes up in a very high current spike. So you turn on the 460 volt, the motor is not turning, so you get inrush currents of anywhere from 3 to 6 times the actual rating if you don't control that voltage when it comes in. And there's many types of older ones that they did. They did it with control transformer. They did it with what they call Y delta, where is the way they configured the winding when they started it with different contactors. And then the more recent ones are the SCR control that I just showed you. So what happens is that we're able to control that voltage ramp as it comes up, and we can spread this out or move it back of how fast we give the motor voltage. The thing that does is it allows the motor to go into more of a slip mode, meaning that you can control, its rate of startup. So this is a waveform example of a soft starter. So if you look at the power here that is coming along, this is the AC voltage. You can see here with the SCR, they start turning it on at a slower rate as the waves are going to it. So the motor doesn't see the average voltage, doesn't see it near as high. So the motor doesn't have that big spike. So you can gradually bring this up, let it operate. And then as you're in this running state, you're providing the full power. You're providing that full waveform, you're allowing it to operate. And then it shifts over and connects directly online. So it's just having just the voltage. It's as a shunt contactor in it, and it allows this motor to see this voltage just as it would directly if they cross the line. Then after you're operated it for a while, and this time ranges, run it for a day, 2, 3, 4, whatever. The reason why you want to buy the soft starters with the shunt in them, because you want that SCR offline. Otherwise you'll have losses, here that are going to, take another 3, 4, 5% of the power. So just shift it off with a contactor, then it's sitting there operating. And then when you're ready to shut it down, you can slowly start bringing the power back on. And so all of a sudden you're slowly starting to regulate the motor again, and that will slow down the motor at a slower rate. And what will happen is then the main factor would be like on a pump, you'll eliminate the water hammer. So you're slow starting, get it up to speed, shift into operation, and then slowly start bringing, the power back down, and then the motor will start slipping, and it'll start, running slower and slower, and then you can just totally shut it off. Another area that I want to discuss is that back to the VFDs that we were talking about is a lot of people have been talking about harmonics. And I want to really simplify what that means. Here's the waveform of voltage that you're seeing. This happens to be a Fluke 434 meter. And it actually is like a oscilloscope. It monitors what's going on. So you'll see here is that as it's given it voltage, and this happens to be the 480 volt, power here, this line here is the current waveform. So you wonder, well, why are those dips in there? Well, what it is if we go back to the circuit here, as these power sources are coming in here, and as it flows through the diode here, when it's going from negative to positive, it flows into the circuit. And then when it gets to this part of the circuit, it ends up flowing the opposite way. And it goes through, another phase and feeds it through. So it ends up creating these ripples here. Well, the issue is that power, the current draw, ends up getting little dipples in it. Here, here, here. Well, from that, you'll see those here. And that's exactly what the harmonics are, is that, so the way they build radios and they great frequency is basically alternating, various frequencies that are sending out, small amounts of power, and it'll actually radiate into the world. So this ends up being, as it's pulling that power, positive to negative, negative to power, whatever, it's actually drawing the power, in current. And so the current, which is the flow of the power, ends up, dependent on the load of that pump motor in general, will start showing these ripples. Well, like here, where you're getting, this is on a 60 cycle power input, you'll see this one, this one, this one, and this one. Well, all of a sudden, that creates 120 hertz ripple voltages on your circuit in current. So you get 120 hertz noise. Well, you also, as you speed up, slow down, all the stuff, these dipples and ripples will go all over the place. And so you'll get a lot of this rippling in here. That's what they're talking about harmonics. They're talking about the current harmonics, which, depending on the strength of the transformer and the power out there, will determine how much these dipples are going to affect the voltage. And so you get what they call voltage harmonics. And so it's very important to understand they will vary depending on the transformer, the load, and the motor load. But I just kind of want to give you a little bit of understanding what is it? Because a lot of people are like, oh, you got to put a harmonic filter on, you got to do da 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 da. It's really understand where they're coming from. So this device allows us to look at all three of those phases, look at all of the wave characteristics of both A, B and C phase, and look at the quality, of that power. Also give us the average voltage between A to B, B to C, and A to C. And so it shows us, that we have right here roughly about a 4.3 voltage distortion. Well, that is roughly about 2%. That's not too much. That's not a really problem. The issue comes in is that when we're dealing with power, my father was a past chapter president of ESA. It was started in 1934, I believe it was, a group of electric motor people. Currently, there's about 3,000 people across the world that are members of this organization, 3,000 companies, I should say, and many, many thousands of people. Well, they've published many, many handbooks that a lot of people aren't aware of or know that they're available. And it's absolutely important that we get this information out, because people today are wondering, why are my motors failing? Why are they burning? We just bought this and ended up having trouble, and we put on a VFD on and it was going to do this and do this. Well, what's actually happening? So the thing that's really, really important that a lot of people don't understand is that when you go look at that ABC phase, which I was showing you here, and if you have more than like a 2%, you only need to derate it. It's down maybe 3 to 5%, which is, within tolerance. They normally have a 15% tolerance, of a 1.15 service factor, so it's not a big issue. The issue is that many, many times today, you'll see as much as a 5% deviation in power voltages between A, B, and C. So what ends up happening is you're supposed to actually derate that capacity to 75%. So a 100 horsepower motor, all of a sudden you only really can pull 75 horsepower off of it successfully and actually achieve without motor failure. It goes into what the nominal voltages are, what the nameplate is, characteristics of over voltage, under voltage. This book is a very useful tool, but I don't think a lot of people even are aware of it. The next factor we want to talk about is motor nameplating. It's very, very important. The issue is always horsepower. You got the nominal voltage that it's rated for. This is the amperage loads that it's pulling. You've got its RPM rating, its frame size, its cycle that it's normally designed for 60 cycle. The biggest factor on a motor is its ambient temperature rating. So it's 40 degrees C. That means that's what it was designed for as outside temperature. Well, the issue is that 40 degrees C, is really only about 90 degrees Fahrenheit. So they really like that motor running in about a 90-degree temperature. The issue is that you can buy motors with various ambient temperature ratings. But a lot of people go, oh, well, I just want a 50 horsepower motor and I want to have it, 1725 RPM. And they kind of forget about what is the actual ambient temperature rating of that motor capability. The other big factor is back to this service factor of 1.15 service factor. I want to bring up an issue about VFDs also, is that when you put them on there, because your output waveform is not perfectly sinusoidal, you lose roughly about 3 to 5%. So you start running your motor automatically into service factor. Sometimes it's 5 to 10%, depending on the VFD that you're using. And another area you want to look at is, it's got a continuous load rating, what the enclosure type is. This is totally enclosed or over. The insulation factor inside the motor, that's how hot it can operate as far as before it starts deteriorating. And so class F is like 155 degree is what the actual stator winding can get up to without starting, major deterioration. A lot of motors today you can buy with class H, but that's not necessarily the best opportunity, because it just means that the motor has this high insulation, but it's going to run really hot. So the other factors you're going to gain is you're going to have more heating in the bearings and those things that are not necessarily already necessary. So, you really want to pick out, the idea would be as a class H insulation. That mean the company's really spent the money on putting high efficiency or high class temperature device in it, but have a low temperature rise. And so that the motor could actually run all the way up to 50 degrees centigrade, which then allows you to be, 110, 120 degrees, and the motor doesn't have any problem at all. You also want to look at that centigrade rating on the VFDs themselves, so those get properly set. The area we also want to then talk about is motor efficiency. the motor efficiency is stamped on the nameplate like 94.1. You also notice over here that at 3/4 load, this motor is 94.4%. So it's actually more efficient only running at 75 horsepower. So it's really important that you find motors that are efficient, but you also have the motor so that it can run down in here, because if you're only running this at 3/4 load, that means this 50 horsepower motor is good for a little over 40 horsepower, but that motor is going to last a long, long time. The other thing you want to buy motors is buy motor weight. If they're cast iron, heavy frame motors, they have a lot of ability to handle a lot of variance capacities, voltage imbalances, and various things that will help us make the life of that motor last. Also, your RPM, different things there. So this is what that meter will also do, is it'll also look at your voltage to ground on phase A, phase B, and phase C. So you can see here that here it's just a little over on phase B, it's a little over 275 volts, but here it's at like 200 and almost 280 volts. So that 10 volt swing between the two operation, and then C phase again was at very pair with what A phase was. So this imbalance in voltage will cause the motor not to pull consistent, and in turn it ends up creating motor problems. This one isn't out of tolerance because it's only 5 volts, but many times it can be much higher than that. So there's also a tool that's out there. It's called this, basically the failures do leave a story. ESA has a product that shows what the motor stators look like when they fail, so you can determine what the root cause of the motor was. This one happened to be a turn failure in one individual phase, so it had a short. This one shows what happens is imbalance. You can see this really charred part here of basically phase A and phase B, but you'll see phase C here of the 4-pole machine has very little heating. So this motor, it was getting proper voltage on this phase, and these two phases, it was basically trying to pull the load, and the current would have been higher on those phases than it would have been on this one. That's why this one never charred. This one happens to be, as you can see, that this is the inner core, and there could have been dirt or scraping or bearing failure that scrubbed, and so it ended up creating heat, burnt the slot insulation, and ended up shorting the winding there. This shows a phase-to-phase failure, meaning that there was a breakdown in this insulation between phase A and phase B, or it could have been C and A, whatever. But you'll see that there was actually a short. So this had 480 volts here and 400 volts there, and it actually jumped across. So it could have been high voltage between these two phases that blew that. This happened to be high voltage to ground, and had a failure in the slot insulation itself, so that it ended up shorting to ground. Again, this is available on ESA.com, and you can get this failure document. The other thing that is out there nowadays are actually the motor manufacturers came up where they're actually making pump motors that are actually designed for VFD application. And the reason for that is that it was more the earlier VFDs, which are straight volts per hertz. They created in the rotor a lot of excess circulating currents because it was volts per hertz. At a certain voltage, it gave a certain frequency. And then another, but it wasn't necessarily linear to what was going on, so to the load. So you could get a lot of extra noise in the motor. Well, that extra circulating current has to go somewhere. So instead of just staying in the rotor, it starts trying to find its path to ground. Well, without any kind of, this is a voltage slinger. Actually, those are carbon brushes that are on this end cap. That gets mounted on there, and that actually rubs against the shaft and actually diverts all the circulating currents that are developing that rotor, goes right to ground, earth to ground, and gets rid of them. Also, they isolate the bearings. They put insulated sleeves in here in the thrust bearings so that you don't get circulating currents, in the upper bearings, and that ends up saving the life of the motor. They also, the type of insulation that's inside the winding, they've went to spike resistant wire that make the motors, end up lasting longer. This happens to be one of the first vertical hollow shaft motors ever designed and built. There's really uniqueness of this, and what they did it for is efficiency, because everything before used to be belt drive, which then you had 3 to 5% loss in your belts, or it had to be a gearhead and then put a horizontal motor driving the gearhead, and then again you had the losses here. Well, they designed the motor so they could drop it right on the top of the pump, brought the pump shaft up, put the thrust bearings on the top, and allowed that motor to carry the thrust, and then there were literally no losses between it and the turbine pump. So the motor ends up being a much more efficient. I also strongly believe in this type of design, other than the verticals, which are the submersibles, where they actually take the motor winding and they stick it down in the water and they put it down here right by the pump. Yeah, it makes it easier to install, but also it cuts the size of pipe that is coming out. So the loss factor between a submersible pump and a turbine pump, these are harder to install, but they do last longer and they're much more efficient. Typically 10, as much as 15% more efficient to have a turbine pump motor as it is to a, the total turbine pump as it is to the vertical hollow shaft that goes on top of the regular turbine pump compared to the submersible. The other area that we want to talk about is the understanding of torque and power, and Rob's going to go into this more later. What happens when you have a 4-pole machine? Here, as I showed in some of the stator windings, they have basically 4 magnets, and so it ends up has twice as much torque as it does as a 3600. As a 3600, which is basically a 2-pole machine. Cheaper to build. These are 1800, but even some of the older ones used to be, at 1200, where they would put 6 magnetic poles in there, and that would give you a lot of additional torque. Compared, it's like 1.5 times, the torque of an 1800 RPM motor. These are some of the standard voltages that we have in America: 208, 230, 460 volt, and 575 and 600 volt power. That's the input power. Again, we want to make sure that we have the proper metering technologies to find out what the true RMS power, is of that motor and application. The ultimate goal here is to slow this meter down. My uncle used to laugh. He said he'd go see people turn motors on. He said, I have to go over and oil your meter. It's running so fast. It does make them run fast. The amount of power electric motor consumes, 150 horsepower motor can provide enough power to sometimes as much as 15 ohms, 20 ohms, the same power use. Thank you. I'll jump back in later, and we're going to let Rob move forward with more details about the use of these devices then on pumps and how they affect the efficiency of the pump to the pump curve. Thank you.
We're monitoring the energy efficiency of all the our major pipeline and pumping systems. Bear in mind that South Australia is the driest state of the driest continent in the world, so we had a very large concentration of water supply pumping and pipeline infrastructure. After that, I went out into the irrigation industry, and that was quite a shock. after spending 25 years in, you know, under the umbrella of professional engineers, to come to the irrigation industry. I got involved in monitoring, more so auditing irrigation systems. Energy efficiency wasn't particularly important when I started, but it has become that way in more recent times. I've been auditing energy now since 2012, and that time I've saved $650,000 worth of annual electricity savings for irrigators. The whole of my career, I've never sold products. So
2016 July.
Yeah, Roger, Roger, there's
Hey, Daryl, your mic is on.
Yeah, you'll have to manually mute people, Roger. You can do that just by going to their window. Yeah, so the feature of my career is that I've never sold product, but I've had virtually a pressure gauge in one hand and a flow meter in the other. So I've been able to see a lot of things that are happening that people that sell product never do, even their own product. So that will provide you a bit of an insight as to what we see today. This presentation goes for about an hour, and it contains a significant number of software visuals, and doesn't include running the software itself. So I'm going to demonstrate the software first. I'm going to minimize that. And this is the software. It's called VFD application, good, bad, and ugly. And it represents a pump curve. Pretty much as you see it. It's got an energy, a pump efficiency curve, and a head quantity curve, and power curves. Now, this particular curve has been set up to run both direct online and VFD. And you can see the two curves at the bottom here, they're horsepower related to the axis on the left. The blue line is the direct online horsepower, and the red curve is the horsepower with a VFD fitted. So when you can see a pump is running at full speed, the power drawn is actually higher by about 5 or 6%. But as we slow the motor down, we'll see that let's just throw that back to 3000 RPM. You can see that all of those lines separate, and you can see a very specific trend. This triangle here represents the best efficiency point on the pump, and you can see that the best efficiency point moves down and to the left quite significantly. And therein lies the issue with VFD application, is tracking where that best efficiency point goes to. So let me just go back, and I'm just going to run through a bit of a tutorial that defines where we're going. This contains over on the left a system curve. So we can add a system curve, and I'm going to add one here. It's a 10-inch pipe. It's 3,600 feet long, and Hazen and Williams value of 150, and it's got a static lift of 110 feet. To help us guide us, we've got some flow indicators. So we've got we're going to run at 1400 gallons a minute. So we've got a fixed flow output, that's 1400 gallons a minute. And we've got a duty head of 140 feet. So there's a horizontal, and we're going to modulate this VFD to run the pump at 1400 gallons a minute down to 70 feet head. So there's our other indicator. So you can see we've got two horizontal indicators here, one at 140 feet and one at 70 feet. So what is the pump horsepower at 140 feet head? Well, if you follow this line down here, it is the red curve on VFD. It is right on 70, sorry, it's the blue curve on DOL. It's 65 horsepower. Now we're going to lower the speed so that the pump curve intersects this point here, and I've got a couple of indicators here. Why is that not working? There, we want to lower the pump curve to that point there. So we'll go up here and I'm going to hit 2875. I've done this before, so save time. So if we slow that pump down to 2875 with a VFD, that pump output will satisfy our 1400 gallons a minute at 70 feet head. If we speed it up to full speed, it'll satisfy 1400 gallons a minute at 140 feet head. So there's the range. Now, what happens when we do this? The power requirement goes down. Okay, so the power requirement is now 38 horsepower at that, and the difference in horsepower between full speed and low speed is 41%. However, we've actually lowered the pump output by 50%. So theoretically, we should be looking for a 50% saving. And you know, VFDs are sold by the cube rule. You know, the power required is proportional to the speed cubed. And literally speaking, if you did compute those speed differences, it would compute to that sort of saving, but it doesn't quite. So we get 50% head reduction and only a 41% pumping cost difference. Now we're going to do something unique. I've inputted this curve. You can see the coordinates of the pump curve at the top, and over here on the right, there are a range of other pumps which we can copy and paste across to this set of coordinates here. But of course, if we want a pump that's slightly different, instead of going looking for a pump in a catalog and copying the coordinates into here, we can change the shape of this pump curve. Now have a look at this. It's pretty handy. We're now going to change the pump duty to 1600 gallons a minute at 150 feet head. So we're aiming, I'll shift this one here. We're aiming for this point here. Okay, so that's still on the system curve. So let's go down here to the modified BP coordinates, and we're going to change this pump to flow C11. Wait a minute, first we've got to change up here. C11 becomes 1600. So these are our new guidelines. That's 1600, and that becomes 150 feet. So that's our new coordinates there. Now we're going to fit a new pump to that point. So we're going down here to change the pump coordinates of the at the best efficiency point. And C37 becomes 170. So you see the shape of the pump change. So we've just now created a new pump curve, and you can see that the best efficiency is fairly off to the left. And I deliberately have done this to show you what happens when certain pump configurations. C6 add 3030, 3030, 3030. So now the bottom performance curve, bottom duty, which is here, is satisfied with a pump speed of 3030. What is the horsepower at 150 feet? It is 80 horsepower. What's the horsepower at 70 feet? It's 50 horsepower. The difference is 37%. So we're actually looking at a 33% reduction in head and we're only saving 37%. So the further we get away from the best efficiency point, the less energy we save with the VFD compared with what the VFD salesman will tell you. So that's the you know, the interesting part about irrigation. We're not talking about following you know, the pump, the performance following the same alignment as the best efficiency point, but we actually force the pump away from its sweet spot, and that's why VFDs don't deliver as much as you're often told that they will. So that's just a brief rundown of the I'll leave that there, and I'll get back to here, and we can kick this off. Roger, are you recording? Hello, Roger.
Yeah, I am.
Good. The good, bad, and the ugly, and will they save you money? We've had a little bit about from Roger, what is a VFD and how they work, and what are the limits of VFD application. We're going to look more particularly at specific applications such as transfer pumps, variable pressure, variable flow, and variable flow and pressure. A variable frequency drive is also known as a VSD, or variable speed control. It's also known as a frequency converter because it changes the motor speed by varying the alternating current frequency, as Roger's pointed out. There's an inherent inefficiency in VFDs, and this data is taken from the US Department of Energy's Industrial Technologies program, and I've graphed the table. So you can see, you know, a typical like 18.5 kilowatts, the thick black line, at a 50% loading, that VFD is only 95%. So you put in 100 kilowatts, you'll get out 95. And if you go for 150 kilowatts, the answer is not much different. Okay, so that's pretty much the limitations of your VFD as far as efficiency goes. If you're reducing the flow by 50%, you're actually down to 12.5% motor loading. And in those situations, you could be as low as only 90% efficiency with a VFD. So, you know, those magical power savings start to whittle away, and not just with the VFD efficiencies, but also with the pump efficiency itself. And that's the major thrust of what we'll look at today. So VFDs come in the same categories as belt drives or gear drives. It's just another driver. A gear drive is 95%. A belt drive is probably, you know, 93%. So a belt drive and a gear drive is between 80 and 90%. A VF drive is between 85 and 95, depending on the VFD size. You know, those lower numbers would be associated with, you know, 1 or 2 horsepower. They're very, very inefficient. If you put a VFD on a gear drive, you'd definitely be below 90% on drive efficiency. So those things need to be taken into account when we assess what our final savings are going to be. Here's a bit of an indication. On the left, we're looking at a pump system, or 3 different pump systems: a single pump, a dual pump, and a quad pump. They're all delivering the same total volume at the same head, but the single pump has a much higher efficiency, the single motor has a much higher efficiency, and the single VFD has a much higher efficiency. You can see here I've highlighted the VFD efficiency in yellow. So 22 kilowatt, 96%, 11 kilowatts, 95%, or 15 horsepower, 7.5 horsepower, only 93%. But have a look how the motors and pumps themselves vary in efficiency, quite considerable. So the combined efficiency, is the bottom line, is significant difference, drops from 69.5 down to 55. So one of the aspects of saving energy is not only the VFD, but the size of the pump and the size of the motor. We cover this in a lot more detail in the pumping system masterclass, which I'm going to show you a little bits of towards the end of this session. So in this particular case, we find over a 25-year life, there is a $55,600 difference between the single pump and the quad pump running costs. That is enormous difference for those size pumps. So there's that's where the good, bad, and the ugly I've categorized as something that's good, it's something that's achievable, bad is not quite as good, and ugly is somewhere you just don't want to go. Let's talk about best efficiency. When a VFD slows the pump, the best efficiency point moves down and to the left. And you can see here, and similar, I demonstrated that with the software when we started. So this blue line is a full speed, otherwise known as direct online. And when we slow the pump down, it moves off to the left, the BP. So you can see the trend as we slow the pump down, our best efficiency potentially moves away from our duty point, from where we want to be operating, and that will detract from your overall final efficiency. So the deciding factor if a VFD is going to save pumping costs depends primarily on where the pump duty point intersects the efficiency curve as the speed reduces. So we've got to, at this point, we've got to refer back to what is the efficiency at the duty where the pump is being slowed to. So we're familiar with this graph on the left. I've just demonstrated it, but let's look at some limits of pump operation. According to your HI 9.6.3 Rotodynamic Pumps Guide, we have some operating regions. We have the preferred operating region of a pump, and it's something like 20% to the right-hand side of best efficiency point and 40% to the left. That's what we should be really striving for. If we can't do it, sometimes the overlap of pump sizes doesn't allow us to get that close. We can go inside the allowable operating range, which extends 30% to the right of best efficiency and 50% to the left of best efficiency. So these limits are both determined by the type of pump, so there are variations. So in keeping with that, we're going to define, for the purposes of this presentation, 3 types of pumps. The type A pump has its duty to the right-hand side of best efficiency point. A type B pump will have its duty at the best efficiency point, and all theory, every course you go to will tell you this is the ideal scenario, right? Always aim to have your pump duty at the pump best efficiency point. But that doesn't apply to VFDs, trust me, and you'll see why. And type C pump, where the duty is to the left-hand side of the best efficiency point. Now, the most common pump you'll see out there is a type A pump. Why? Because if you call for a pump of a specific duty, you'll find that this configuration here will be the cheapest pump to sell that will give you the duty that's required. And so that pump tends to be a smaller size, whereas if you go to a type C pump, that pump will generally be much larger and therefore more costly. So on a competitive basis, competitive tendering basis, you will find that the type A pump will be the most common pump in the irrigation industry, where the duty is sitting to the right-hand side of best efficiency. There you go. One of the things we look at is how to calculate the cost of power, and we do that in terms of kilowatt hours per acre feet. And here's the formula in US units: 1.024 times feet head, total dynamic head, divide by the drive efficiency, and that's taken from the NRCS book. There are 3 very important components of this that we're interested in. In using a VFD, one of the main aims might be to reduce the total dynamic head, and the other, we need to look at the pump efficiency, and we need to also take into account the drive efficiency. So there are three areas that we look at that will determine largely how a VFD will perform and how much savings it will derive for us. Why use a VFD for irrigation pumps? Well, we might want to have variable flow, you know, and this would be typically turf orientated. It's common in turf and landscape. We have multiple outlets randomly coming on, although they are programmed, but they're randomly coming on. And it's great for improved CUs and DUs and crop productivity, but it doesn't save much energy in variable flow situation. Variable pressure, this is more ag, where you have the same flow, but you want to vary the pressure. You might want to change from you know, one type of emitter to another, or you might have a variable elevation situation with a center pivot. And then there's, of course, the booster application. So we look at these four common scenarios: the transfer or reticulation pump, variable pressure in turf particularly, variable pressure in ag particularly, and a variable flow in turf. Then you get the mixture of those two. Let's have a look at a transfer pump application, you know, typically with a near zero or zero lift. And it's open-ended. It might be a transfer pump from a river to a dam with very little lift, and it might be solar powered. In this particular case, as you speed the pump down, as you slow the pump down, the best efficiency point goes right off in an exponential curve back to zero. Now, if you were to plot a resistance curve or a system curve for 2,000 feet of 3-inch pipe, it will follow almost the exact trajectory of those best efficiency points. So you can see that's the absolute perfect application for a VFD, and you'll find, you know, a lot of the big savings, and Roger alluded to those big savings, occur in industry where you have a zero load at zero flow, and these situations don't exist in irrigation. Okay, so this is a particularly interesting one. It's just a transfer pump, and you can liken it to a lot of the applications in industry. When I say industry, I mean other than the irrigation industry. So in this particular case, a type B pump, you know, where the duty point is right on the best efficiency, is the perfect type of pump to have. And this might be a typical scenario here where you have a solar powered system, and you know, you can only pump as much as the available solar energy allows you to. So in this particular case, it is the perfect application where when you got you know, morning and early morning, late afternoon, the pump output is only low, but it's operating at best efficiency point. So that's what I call a very good application for a VFD. And the VFD is an integral part of your solar system, where it's an inverter is required to convert the solar from DC to AC. So a solar system automatically includes a VFD. What if we want to lift water a little bit higher, you know, say from, and this might be another solar application, for example, from a shallow well to a tank. So now you're starting to look at some lift. So if you look at this curve here, the broken blue line is the system curve, and we might be starting off of the 35 feet lift. And if we use a type A pump, where the duty is to the right hand side of the best efficiency point, we will start off at this point where the the efficiency is down to the right hand side. It's on the falling side of the right hand side of BEP, and when the pump is operating at its slowest point, it is followed the best efficiency point over the peak and down the other side. So pretty much, you know, the starting and finishing points is as low as it can go. Everywhere in between, it is a higher efficiency. So I'd regard that as a very good application. But what if we were to look at a type B pump for this application, where we start off with a pump at best efficiency point at the duty point? Well, it works fine at the peak duty, but when you slow it down, the efficiency drops right off from 82% down to 67%. So that's not particularly flash. I'd call that bad. But even worse, what if we went for a type C pump, where the duty was to the left side of the BEP? And here we're already seeing at peak duty, the efficiency point is already on the downside from the speed curve, and by the time it gets to the lowest output, we're well down into the 50%, and I'd call that ugly. That's a bad application. So as soon as you start applying a VFD to interesting applications, you really have to look critical at your pump configuration before you start to know what you're going to finish up with in the end. So in summary now, a type A pump, if we just look at the speed change alone, we will show a 53% saving. And this is what the VFD people will tell you, change the speed, it'll yield the cube of the speed change. Well, that's 53%. Now, in this particular case, I've calculated the actual energy savings, and it is actually 53% because it started off at the same energy pump efficiency as it's finished up. And then we go to the B, pump B, and it's less, but pump C, type C, the speed change only required 27%, but it only saved 19% in energy. So pretty much, there's your type A pump, gets the big tip for this type of application, and type B pump bad, and type C actually quite ugly. Didn't really save that much energy at all. But variable pressure, the classic situation might be, for example, if you've got a center pivot, and the center pivot traverses some undulating ground. And typically when it does that, you would have to configure the pump to provide the minimum residual when the end of the center pivot is at the highest point. Of course, that means when the center pivot rotates around away from that point, then the end of the center pivot will be lower. There'll be much higher residual, and that amounts to wasted energy. Now, we account for that by putting pressure regulated emitters on the center pivot. It doesn't stop there being wasted energy. So what we can do, we can install a pressure like a portable battery powered pressure transducer with a telemetry system at the end of the center pivot, and we can telemeter that back to the VFD at the pump. So as the center pivot goes around, we can harness that energy waste and slow it down with a VFD. But in so doing, what's the best application for that VFD? So this is taken from a case study I did, and so if we start off with a type C pump where the duty is far to the left of the best efficiency point, so in the first instance, we're going down the aisle. Remember, we're stuck with the same flow rate. In this case, it's 250 gallons a minute. So the efficiency at full load is on this blue curve, so it's 76%, and the efficiency at the reduced load, well, hey, look at that, it's actually higher. So as the speed of the pump come down, the actual efficiency of the pump went up. So it works in our advantage to have a pump of type C, and the savings in this case, 49% of the highest point compared with the lowest point. But what if we had a type B pump? So a type B pump would start up here, best efficiency, and then finish up at a lower efficiency. And the savings in this particular case is only 42%. What if we went for a type A pump, where the duty is to the right-hand side of the best efficiency point? Now, bear in mind, this is more than likely the most likely pump you'll find in the field. And this one spells disaster, really. So you start off with an efficiency point that's already falling on the right-hand side, and you drop the head down at that same flow rate, and so you're down to 60%. So that's a particularly ugly situation. You would not want to use a type A pump on this particular application, which is variable pressure, constant flow. So, you know, just looking at that last slide, we may want to, if we consider an envelope of operation of the VFD, of pressure and flow, we would want to block out any pump that's operating in this zone if it is a type A pump. The type A pump is where the duty is to the right-hand side of the best efficiency point, and this is for a variable pressure situation. So here's the summary. The type C pump was the best, where the duty is far to the left of best efficiency point. That usually is the more expensive pump to provide, but in this case it's well worth the money. It had a potential saving of 58, but a real saving of 51. The next was the type B pump, where the best efficiency point is the same as the duty point. That only realized 42%, and the type A pump, disaster situation, only 32%, and the potential to run the pump off the end of its curve. So here's a bit of a summary of that potential savings from a center pivot with a remote pressure transducer telemetered back to the VFD. So in this particular case, we're delivering, say, 81 acre feet at 34 cents a kilowatt hour. The head saved is the difference, half of the difference between the highest point and the lowest point. The highest point is 745, the lowest point is 663, and that is a distance of 82 feet. Okay, that's the elevation, but we can't save the total of that. We can only save half of that, because on the average, the center pivot will spend you know, a little bit of its time right at the top, a little bit of its time right at the bottom, and the rest equally distributed halfway between those points. So we can work on an average saving of 41% feed head here, and from the formula above, if we put in those details, we're looking to save $1,764 per annum of electricity. If we add the cost, that's the OPEX. If we look at the CAPEX, what are we going to have to spend to achieve that? We need a pressure transducer, a kit to go on the end of the transducer, end of the center pivot. That'll be about 2,000 fitted, and we need an 18.5 25 horsepower VFD, say 4,000. So that's a total CAPEX of 6,000. Divide by an OPEX of 1,764. That gives you a return on investment of 3.4 years, and that's pretty good. You know, that's really well worth adopting. However, it does point to the fact that, you know, the RPM rule does not apply here. It applies for a specific elevation, but overall your savings do not equate to the RPM cube rule, as the VFD industry would tell you. What about if we want to have a situation where a pump is delivering much higher head than it is required, and the irrigator puts a throttling valve? You know, it might be a butterfly valve or a gate valve, or even a hydraulic valve with a bonnet and a membrane. we normally regard those throttling valves as energy wasters, and if we can do away with them, all the better. So, you know, the industry would say, well, fit a VFD. Well, that's great if we could do that. So here's a scenario. It was a real one that I saw. This is the system curve here. Follow this thin purple line. That was the pumping main to a center pivot. Okay, and this is the pump curve here that was feeding the water. So that was the duty point for operation to the center pivot. Now, when that pump wasn't required to be pumping direct to the center pivot, water was diverted from that same rising main to a dam, and from a river system which had to be pumped from only when the river was flowing. So, you know, the water authorities say you can pump from this river system from you know, November to end of February, and so during that period you pump like mad so that you can get as much water you can within your allocation, of course. So what this farmer did is, instead, when not pumping to the center pivot, he would throttle a valve, and this system curve here represents the same pipeline to the dam. So we've got a much less lift. That's the only difference. The resistance is the same, but so if you put a throttling valve on there, you can still maintain your 75, or, you know, around about 1,000 gallons a minute. But what happens if you were to put a VFD on there to achieve that same, you know, and save the energy wasted by the throttling valve? Well, if you applied a VFD to that curve, the end of the curve goes down in this direction, and there's the pump curve at the first opportunity that it contacts this system curve to the dam. And at that point, we're only pumping 500 gallons a minute instead of you know, 1,200 gallons a minute out here. So the farmer is not achieving the ends. He's not getting the pumped flow because of the effect of the VFD. It actually slows the output. So in this particular case, the VFD just doesn't work for the farmer. Yes, it will work, but he'll only get 1/3 of the flow rate out, and therefore he won't have the potential to gather the amount of water that he needs from the river when the river is running high. That's a particularly ugly situation. If you wanted to apply VFD, you just wouldn't do it. The ultimate solution to that is a separate pump with a lower head. That's really the only solution. I just want to show you, this is something that I saw on the internet. Here's somebody's portrayal of a pump curve at full speed, and here's the pump curve at a reduced speed. Now, this doesn't show any movement down and to the left, you know, so that pump curve on a VFD shows that you can pull the same flow just at a reduced head. That is totally wrong. It is misinformation. You really have to be careful when you look at some stuff on the net. It's just wrong, okay? It's a bit sad because I wished our VFDs would work this way. You know, they'd be worth $1 million, honestly. What about variable flow? You know, this is a scenario where we have turf often, but it could be ag, but more common with turf. Let's start with a type A pump, the more common pump that's out there, where the duty is to the right-hand side of the best efficiency point. So we start off here. So there's the full speed pump here. There's its best efficiency point, and this is the duty. So we're now looking to run this pump in this area of flow at that same pressure. So we start off with a running a pump efficiency of 68%, and we finish with a pump efficiency of about 66%. That's a pretty good balance, and everywhere in between there, the pump is running at a higher efficiency than that. So that's a big tick. That's an ideal size, ideal type of pump configuration to satisfy variable flows such as you would get on turf. What if we had a type B where the best efficiency point is at the duty point? We start off with a best efficiency a pump efficiency of 70%, and we finish up with an efficiency of 50. So I'd call that a bad situation. Definitely not as good as it could be. And lastly, if we had a pump duty point operating to the left of BEP to start with, so here's BEP, and here's our duty point here. So full speed pump efficiency is 68%, and when we throttle it down, the pump efficiency goes down to 40%. That's particularly ugly. You would not want to do that. In fact, you could potentially be operating the pump in a harmful area. So with this particular application, we would like to have a no-go zone in this area of operation for a type C pump on variable flow. So in summary now, the type A pump is the best here, where the duty is to the right-hand side of best efficiency. The type B pump I'd consider bad, and the type C pump is definitely ugly. Okay, let's look at the real energy savings. Even if you did save 20 or 30%, and I'll get back to a presentation I saw just a few months back where a large pump company was giving a spiel at the end of a presentation at a council, recently completed council irrigation works, and there was a whole group of people were invited to celebrate the occasion. And the pump company guy got up and said, of course, these pumps are fitted with VFDs, and you'll save at least 35% energy with these VFDs. And I'm thinking, how bad is that? Well, yes, at the slowest flow, you may save that amount of energy, but how much time are those pumps pumping at that low flow? Let's look at a typical breakdown. You might find, I'm not going to start at this point, the highest flows are where the system duty point is. You find that a typical turf system may be pumping at the highest flows at least 50% of the time. And I've calculated, in the previous example, previous pages, that's 431 kilowatt hours per acre feet. It might spend 40% at medium flow rates. That's only 490 kilowatt hours per acre feet. But the really low flow rates, where you can get the best VFD energy savings, it's only pumping 10% of the time, sometimes even less than that. So we have to find out what the real savings are, we need to create a weighted average cost. That's otherwise known as an annual specific power input. So it's 10 times 801 plus 40 times 490 plus 50 times 431 divided by 100. And the answer is 492 kilowatt hours per acre feet. So that's the overall consumption. Now, if we compare the energy savings at 801 acre feet, represents 41% savings. So I'll just go back. So that's here. This is the good one here, where the pump operating best saving scenario is from 801 to 469. It represents 41%. So if 801 kilowatt hours represents 41% saving, then 492 kilowatt hours represents only 7% saving. So 7% saving is all we're going to achieve on a VFD system on turf. So forget about your 35%. It doesn't apply. It doesn't apply. So your RPM rule is really invalid. I mean, it's valid if you consider the energy savings when the pump's running real slow, but it's like saying about your motor car. Your motor car gets 100 miles a gallon when it's only traveling at 5 miles an hour. Well, big deal, because how often do you do that? Well, 95% of the time you're traveling at like 60 miles an hour. So tell me, What's the average? Okay, that's what we want to know, is the average. So the real benefit of a variable flow with a VFD is not energy saving. The real benefit is pressure, is regulated pressure, and it is it's irrigation efficiency or crop yield. That's the real benefit of VFDs for turf. Forget about your energy saving. There's not much there. Okay. Let's have a look at a graph of energy saving. If we were to draw a power curve for a normal pump, so this is your head quantity curve, the blue curve here, and this other blue curve with the square dots represents the power over the range. And if we were to put a VFD on it at this point, at the with a type B pump, and run the pump at a constant pressure along this line, this would be the energy saving in here. So it graphically demonstrates, most of the time in a turf situation, we're running the pump system up here, and so there's no tangible savings at all for 90% of the running time in a turf situation. Where you do benefit is that you don't get over pressurization, therefore misting and water wastage when you go down to the lower flows. What about a combination of variable pressure and variable flow? Well, it's really a combination, and you might recall we had a no-go zone for a variable flow and a no-go zone for a variable pressure. So if we combine these variable pressure, variable flow situations, you'll finish up with both of those no-go zones, and it's safe to operate the pump in the rest of this area as far as flow and pressure goes. And you might have situations like that in an elevated site where you have multiple outlets, and the outlets are of different flow sizes, and that's all by design, of course. So if you're going to design an irrigation system to be run on a VFD, it might be prudent to actually size those outlets according to what you're going to be able to achieve when you run that with a VFD, and it needs to be inside this zone and not include the red bar zones. In this particular case, it is the type B pump where the best efficiency point is the same as the duty point, is the best. So let's look at, in summary now, the application and the pump type. Our transfer, low lift, sorry, the type B pump is the best, where the duty is at the BEP. If we are looking at some elevation to lift the water to, then we need to go to a type A pump, and that's for low level lifts. If we look at variable pressure, which is a typical ag, so your constant flow, variable pressure, you definitely need your type C pump, where the duty is to the left of the BEP, and you will have this no-go zone where it would be dangerous to apply the VFD to that area. The variable flow is your typical turf application, and it may be some ag situations. The best type of pump is the type A, where the duty is to the right-hand side, and you will have a no-go area on the lower flows and lower pressures. And lastly, the variable flow, variable pressure. The best pump would be a duty at best efficiency point, a type B pump, and you will have these no-go zones where you won't want to go. Now, not to say you can't go there. If you go there, two things will happen. You'll significantly reduce your energy savings from the application of the VFD, and you will expose yourself to damage of the pump. So that gets back to, well, how do we ensure that you're going to get value for money when you install a VFD? You really need to go back to the basics work out what pump performance you have, what the duties are, and use this type of software to run it through the paces. Set your pump to work on this software before you even think about putting a VFD on there. And this particular software, you can add multiple pumps. You can add 2 pressure limits, 2 flow limits, as we're seeing. There are 2 system curves. I'll go back to the software in a moment and show you a couple of more features. To add a new pump curve to it, you print off a pump curve from a family of curves and identify 7 operating points on the curve, and note the coordinates and simply add the coordinates into the Excel matrix. It's important that that the 5th one, starting from 1, 2, 3, 4, 5, the 5th one is always at the BEP, best efficiency point, and I'll demonstrate that why in a moment. So your traditional VFD promotion says this device will save you up to 50% of your energy costs. That implies that you're pretty much always going to save energy. What we should be saying is this device may or may not save you energy. That's the reality of using VFDs for irrigation. If you really want to save energy, we should be looking further than VFDs. We should be looking at what's inside the Pumping System Masterclass, and that's the other major course that we run, and it is aimed specifically at saving large amounts of energy on irrigation systems. So let me just briefly tell you a little bit about this course. This course teaches how to design pumping energy efficiency principles into new irrigation systems and to fix old ones. It redefines pumping energy efficiency for irrigation. It empowers the participants to save thousands of dollars on pumping costs, literally. And it provides numerous software in addition to what we've seen today. It has 7 other software packages which really empowers you. Now here's some comments from people who have done it. You know, Matt Angel from Madeira Pumps said, Robert, the class was amazing. Every pump engineer, equipment specifier should attend this course. There's Terry Rouge. Now Terry was due to be with us today. I'm not sure whether she's made it. Hello Terry, if you're there. She said, Robert, there's not a course like this in the United States. Indeed, there's not a course like this anywhere in the world. This is unique. And a guy from New Zealand who's responsible for irrigation design policy said this course was excellent. It has definitely raised the bar for New Zealand irrigation pumping design. So yeah, that's the story. And there's the suite of software that comes with this, that if you want to save energy, this is the way to go. VFD is just dabbling around the edges, honestly. Applicable in certain instances, but if you want to save energy, do this course. And it's got 4 modules, and each module might look like familiar modules with normal pump training courses, but the application of each module is entirely different. You will be amazed. Okay, that's the presentation. Let me just go back to the spreadsheet, and I'll show you a couple of extra features. We can drag over, for example, if we want to change the pump, we can just copy that whole amount there and drag it and put it over to here. And we've changed that pump. It was a Gould's vertical turbine. Now it's a Grundfos 60 Hertz. So you can build up your own library of pump curves on the right. But the beauty of it is you can change the configuration of the pump. So if you're designing a pumping system that needs to operate on a VFD, you can import a pump curve that's around about the mark, and you can massage it. You know, say for the head you want a 250 foot head instead of 170, and it will produce the pump curve at that higher head. Then you can start playing around with it. You know, obviously the static head will be 200 feet. So so there's so much flexibility in this software. In the end, you'll come up with the ideal performance of pump that you need for the job, and then you print that out and send it around to your pump suppliers and say, what's the best you can do for this, you know, to closest to this pump curve. And you'll get feedback pretty quickly. Yes, I can. No, I can't. And whatever they supply the closest, you're going to have to put back into this curve and see what the limitations are for your VFD application. You have to bear in mind the type A, the type B, and the type C for each type of application though. So it's not easy. It's not simple, but it's doable. And this is the software that you can do it on. Roger, thank you.
Yeah, thank you. That load, look at that pump and determine where we are as far as actually really true RMS kilowatts used. Let's see. This is something that I think I sent out to everybody, and you're welcome to have it. It was a free tool that Rob was willing to share. And it kind of gives a very nice, and you can actually download this to your iPhone, and you can actually put in some of these parameters of, you know, what your pump head is. This is before anybody does anything. You know, find out if you do have just a belt drive or whatever it is you can put in a VFD or not. You can find out whether it's a submersible pump, because a submersible is on average about 10 to 12% less efficient in the amount of kilowatts it uses per horsepower, per total horsepower. So you have a loss there. You can put in the amount of water pumped. You can look at your pump duty, which comes into a 75%, and then you can actually go to your power bills and accumulate out of the power bills, what your total kilowatt hours were used, annually. Put in your annual utility rates, and then it'll automatically just run a quick test for you for that pump and see if there is any potential look at savings, if there is some losses or not, and it's a kind of a simple operating tool. Rob had the software he talked about, basically, which was the Excel, which I highly recommend, so that if you're going to be selling VFDs, you're going to be putting them in, you should be getting with your pump people, get the pump curve loaded in here, and then look at those different set points before you go ahead and stick the drive on. I've seen way too many VFDs, put in, and they can't really even bring it off of, maybe run to 55 hertz. And then all of a sudden they stop pumping water, they start cavitating. So this just gives a modeling tool that helps you, in advance, kind of look at what's going to happen, and or maybe even if the guy needs to change the pump, he should be doing that in advance. I also will send you out a software tool that allows you to take and put then the data of from here, that when you're going to use it at what time points, and then do a modeling of the VFD of what you're going to truly save in energy. So you're putting the proper data, from the pump into the VFD software that come from the VFD manufacturer, and you're ultimately then going to see, a much better reality of value of savings. If you do want the software and the details here, Rob has allowed that he'll give you all the curves and the IPEC software, for the key. And he does, he's got to make a living too, so he does charge $49 to get, access, and then he does updates. He'll give you, copies of the software itself for that. Then I do want to, put a plug in for his, water pumping software masterclass. I've taken it 3 times. I've been quite shocked at the additional things that I've learned, and have been in the industry for a long, long time. And it really, really does help understand, pipe and, all the other pieces. And what that actually comes with is he's got these 4 software suites, which are basically the pumping it, one that I showed you that he gives away. Then he also has this assessment tool that also ties it back to the the actual pump in further detail and additional on-site tests that he recommends that you take that. Then he's also got the what they call is hydrox. You can probably jump in and say the names, what you call them, more than I do, Rob. But
hydrox.
But basically, it's so we can actually look at the pipe diameters, because I was, flabbergasted by the difference in even just a 10-inch to an 8-inch pipe over a long distance, with the Hayes and Williams loss factor, because the pipe was older, how much loss was happening just in the pipeline. And so one thing we had talked about is that, there are additional savings sometimes once you get all of this down, where you might just want to slow the whole hydraulic system down, get it back to best efficiency for the pipe, and get it also back best efficiency, for your pipe calculators, and also all your pressure your regulators and head pressure, through valves, through filters and all those things. And that's what he goes into in his master class. This is more in the curves that he has in his master class, which he basically gives you your pump data calculator. He's got the pump testing templates, and I just highly recommend that. He does charge us $550 for that, but I think it's more than worth that that value, because it shows all the in-depth spots where it can save. The other thing that we go into also is we talk about, demand charges on your power bill. The difference between KVA and KW demand, time of day, when you get charged demand, typically in the United States is after a 15-minute period of a given load for that 30-day period. You get stuck with that demand, and whether it be high, low, or during the different peak periods, and then they keep track of it. The proper understanding of before and after calculations on power use. There also are a lot of federal and state rebate programs out there. And I believe
this particular tool here, of course, is based on pump manufacturers' curves, and there is potentially an element of overstatement in them because of the way pump systems or pumping curves are defined in the pump test code. So we deal with this in a large degree in the masterclass, but you might actually want to over specify a pump because the pump you get delivered may underperform.
It's a great
by
call.
how much? By how much? You don't know.
Yeah. Well, the twist comes is, typically, let's just say that we've transitioned a lot of motors, right? And we've transitioned them in both ways. Both up, where we were pumping more water, like pre-12, pre-13, and then now we've gone back down in horsepower, right? And so what's happened to us is that, we're still using, if we're pumping, and what's happened is our pumping water levels are deeper, right? So those aquifers may be less efficient, our perforations may have never been developed. So we've got well efficiency tied into pump efficiency, and unfortunately we're gauged on motor efficiency when we do a pump test, right? And
yes,
and it's an interesting concept, but well efficiency far out exceeds pump efficiency when you start talking about power and all those things. And the deeper we go, the less efficient those aquifers are. The bigger shaft we have, and there's just more, there's just more draw on these motors. So what happens to us is that if we over spec, here's how this is what a grower typically comes into me. Got a 150 horse motor, and he says, hey, I need, because we've gone, our water table's declined. I need more water, or as much water as that pump will give me, right? So depending on the time of the year, you know, right now we're hedging our bet with the dry season. So what happens to us is if we over design and we push that pump a little too far, now we're over the, you know, the power factor on the motor. It's over amping, you know, so, and we probably design that pump and motor to maximize or max out the kW on that transformer. So it's a fine line that we're walking out here, you know what I mean? And so what I guess I'm asking is that, and I get what you're saying with that master class, it's going to be critical for me, because I think it's so important to know every dynamic that goes on other than motor. I need to look at well efficiency. I need to look at pump efficiency, and those three in combination, I think we're going to have to tear down, and then throw a VFD in there. And what we've been trying to do is that we'll lift a surface on some of these pumps, and then we'll put a centrifugal to build pressure, and we'll run it with a VFD. Yeah. That way in the spring we can crank it down, and then in the fall we can kind of crank it up. But we got to be careful there too, because if we start pulling too hard with that booster, now we're wearing the bearings out on the top end of that pump. So it's an entry. I tell you, Robert, you have come at the exact right time with this program, because it's something that I think people need, and I think we all need to understand. And the state of California needs to understand it, because in their suite programs, if you look at an index, right, just like NRCS, you get a certain amount of points for doing a feature, right? So the CDFA has decided that in the suite programs, if they put a VFD in there, well, you get 5 points for the VFD, even if the VFD is not needed, and it actually takes more energy to use, right? Yeah. So we've got this real fine line, and I think, you know, I look at what ITRC does over at Cal Poly, and they've been pushing pretty hard on the VFD side, but we've got some big work out here that we've got to do. And I think in California is going to set precedents across the United States, across the world, you know, because there isn't anybody that's not in the same conditions that we're in.
Yep, I sense that, Matt. Thanks for that. You've got unique situations there, especially with a receding water table. It's just dynamite to a pumping system, and I'm pleased to hear that you're tending more now towards dumping the water at the top of the well and relifting it with an end suction. That's the perfect scenario for any well pumping situation. In Australia, here we've got a more unique situation where there's hardly any vertical turbines. Most people use submersible pump motors, and they're 10% less efficient. The motor itself is 10% less efficient than a surface induction motor. So you have already, you know, even not considering reclining water tables, you have already a 10% energy impost by using a submersible pump motor down a well. There's a whole heap of factors, and these are all covered. You know, I cover these in the masterclass so that you can get a handle. It is totally empowering. You know, you come away from this course saying, man, I can handle. I had a guy come back and said, Rob, thanks for this course. I can now go to site and handle anything a farmer throws at me. I thought, that's fantastic, because they can throw some really curly ones at you.
Well, the time I've been hanging, you know, Roger's been hanging out with us for about a year, and you know, since you and Roger have met, and we've been plugging in with you, Robert. It has been, you know, eye-opening, and obviously for us, where we're headed, both from an energy perspective, greenhouse gas. You can go right down the line. You know, there's a big push on optimization that we've got to achieve. And, you know, up to this point, our system and the way we've been chasing water has not been conducive to you know, it's just, there's just a lot of work. So I'm hopeful that, you know, that we can get, you know, as we do more of this work, Robert, that you know, we just keep getting better and better at this.
Yep, it does. It gets better in time, and until yourself you feel like you've reached the sweet spot, and that's it's an amazing feeling. Mind you, there's always something to learn. You know, the more you know, the more you realize that you don't know. That's the scary part about getting older and learning more, is that, oh my God, there's so much more to learn. And so you're on a constant learning curve. We're all on constant learning curve. So thanks for that.
It was extremely helpful for Roger to talk about, you know, the stators and exactly how a motor starts. I think you guys need to keep working on those things so that we can see cooling effects in different types of motors. I think we ought to be putting a big push here in California. I mean, one of the things that Roger saw last summer with us is to put covers over bigger motors. We're trying to encourage our growers on a motor that's over 125 to put a cover on it. You guys probably have done that forever in Australia. And then I was really encouraged by the fact that you guys are breaking down PG&E's rate schedule. I think that's critical for growers to understand it, that demand charge up front and how important it is. If we can get more growers to understand that, that'll help everybody.
Yeah, a demand charge, you know, you can take an awfully large advantage from a demand type tariff, but you have to really understand it and be prepared to shut your system down early. Yeah, that's just a comment. We're starting to get demand charges becoming more common here in Australia, and as we adopt more solar, that will be the case. You know, that we just don't have the stability of the power systems like we used to, and there's, you know, early uptake of batteries in Australia are trying to pick up the difference because they're instantaneous. Oil, you know, coal powered stations are closing down, and that's more to do with their age and than anything, and it's not viable to build new ones. So, you know, there's a whole area, and Roger's already alluded to this, that the enormous effect that this unstable grid voltages and currents can have on VFDs and even motor power. You know, one of the curves he put up there is, you know, something like a 5% variation in phase voltage can result in a 10% or even more reduction in your service factor. That's amazing. And you know, I go to site, and just about every site I see as much as 5% variation in phase currents. You know, so it's out there. It's almost an inherent part of systems. We get feedback again.
It must be me.
Yeah, it must be you, Roger. You got to switch.
No, he's on his cell phone. Hey, I got a question for Roger. Roger, one of the things, you know, with our software, you know, we're plugging into the Modbus on a VFD, and one of the things that I wanted to hear is, off of a motor, you know, when I start looking at a VFD and I'm gathering data out of that VFD and monitoring it, what are the things that I should be looking at in that motor that I can see coming out of the VFD?
Well, the VFD also, it has way too many parameters. There's like 250 of them in there at least that you can adjust and play with. And most people that use them probably end up using about maybe 5. And they don't set all the limits and the details. But what you're saying is they have, you know, built in a metering, so you can look at all of the input voltages, the current flows to the motor. You can calculate the motor temperature, you know, based off, because these devices are so much further advanced for application. They're using them for, you know, high-speed spindles, high control, and it's the same control. So they have all of that software in them. But what I'm really trying to get out is the understanding of how to use all those tools, get them to the Modbus connection, and get the data, records, of what's going on. You can look at faults, you can look at high voltage, low voltage, all those details, and take those motors offline when they're actually, running those imbalances on the inputs. And so that's what I'm trying to bring forward. Like I said, I've spent so many years in motors. I can't even remember. I mean, it's not like 10 years old when my dad started me winding them. But then to see the actual failures that are going on because, everybody went high efficiency. Well, what that did is in an ag application, you're out in the middle of rural and you've got all of this, voltage imbalance and high temperatures. And so we're not in an ideal location. That's why that old motor, that I showed you the first, vertical hollow shaft on that drawing, that motor was probably 3 to 4 times the size per horsepower of what we're putting out today, as far as the same frame size. So it's really important to buy those high service factor motors and also make sure that they have split cores like the older ones did so that they can actually cool them, especially in rural application, and then also be able to handle all the humidity, high altitude, and various things. It's just that too many things have gotten stuck into, well, we're in an ideal world and they're using, industrial rated designs to build motors today for ag applications, which have always been inherently, not easy. I mean, they're just not easy. Maybe a long line, you get a lot of drop, voltage down, the line. So, the motors are coming out 1.0 service factor, but you don't realize, and then put a VFD on it, you should really be minimum of 5%, a service factor loss that you're going to get by putting a VFD on, just because the output waveform is not sinusoidal, it's pulsed. And so that's going to create, a current waveform that looks, sinusoidal, but it just creates heat. And the first VFDs you always heard were like the carrier frequencies that were, like maybe a 500 kilohertz, meaning 5,000 pulses per wave to build it. Now they're up into the 15,000. You don't hear it, but it also creates a lot of extra radiated frequency. It's just like an antenna that they're running down a line, and you actually hear it on an AM radio, and people don't know where it's coming from. And so that's what I'm really trying to bring forward is the actual. There's huge benefits. Don't get me wrong. I mean, they will. I mean, like Matt, a couple things we did where we helped the guy. He just couldn't get enough GPM because his water level dropped. You were able to speed the pump up, overspeed it. Looked at the tolerances of where you can do it and actually get the guy to trouble without having to pull the whole well out. And that's where I think the more and more we can educate it, but also keep it simple. That's why I wanted to bring it back to we're just controlling that rotating field, that Tesla designed a long time ago. What he figured out was phenomenal, but there seems to be all of these buzzwords in the industry that put a lot of fear into it that people don't then feel comfortable using it. Or, you had told me once they put, like it costs like what, $20,000 to put on that 350 horsepower to put a harmonic filter on, and to understand whether you're truly needed it by, how to read it and measure it, and then, then put it on and see if the power company, will actually approve it, or just totally stay away from it and design your whole pump, design and system and just put a soft start on, but you got to size the soft starts even right to make sure that you're going to have the motor be able to basically, because what you're starving it, you're giving it full frequency, but you're starving it with slip. So the motor, certain soft starts will not give you that long ramp time, on a pump application that you need to eliminate water hammer. And then, Rob has shown me a lot with these, pressure regulating valves that, there's benefits by putting VFDs in and running that, where you don't need the pressure regulating valve, but it's taking the whole system together for efficiencies, not just, okay, I'm going to give you a silver bullet and put a VFD in and your problems are going to go away. Well, sometimes they get complicated. And that's what I just don't want to see. And I think that it's the more and more we can, bring that forward, the better off we're going to be. So.
Well, that's a great point. And, one thing is, Roger, is you talked about it. I think our understanding, I think what happens to us is that we're educated, from a pump perspective. Our source of education comes from manufacturers, right? And we were lucky to have you roll in, because I think that, that was a bit of a game changer for us. But you started from square one and started talking about, the heat transfer in a bigger casing motor. That's why the old school, like a Newman or something, had longer durability, because it had more metal in it. It could dissipate the heat. All those things, I think, were really important. And so, as I look at this, I mean, I think from an electrical standpoint, I think we really need to, I think, you guys in this class, I think that needs to be emphasized. But even the simplicity of the fact that, a guy will walk in and you'll start talking about chokes and different things on a VFD. And simply put, that choke is basically going from AC to DC back to AC, right? And the ironic part of it is that everybody has a different name for it. There's all these acronyms, like you said. And I think if I was to encourage you guys to do something, it would be to build a vocabulary and show some of the things that you showed today, so that people, I see Justin Wiley on here. It would be incredible for Justin to be able to look at that information and then be able to have a conversation with us. And then together, we looked at the best solution, that would work in his environment, and what we could do to give that asset better longevity and higher performance.
Yeah, I think definitely the part about, creating a vocabulary, and that's something I've always really tried to do, is to simplify it, because you can call it a link choke, you can call it a line reactor, you can call it an inductor, they're all the same thing. And so, the difficult driving factor of too many products, not only the pumps, the VFDs, the motors, the pipelines, all of it is a building block